All right, so when we take a look at this area here, the question is, what is the area of this disk? Well, I like to think about, anytime anybody asks me about the volume of a cylinder, I always think to myself, if I want the volume of a cylinder, don't I take the area of the top of the cylinder and multiply it by its height? So what's the volume of a cylinder? Isn't it a collection of individual areas that are stacked up on top of each other? Just like if I go to the deli, I see little slices of bologna or salami or cheese or whatever you are. Can I take those and stack them back up and get back to the original size or volume of the cylinder? Now there's an interesting thought here, same process. If I want the area of this disk, isn't this disk a collection of thin rings? So when I think about the area of it, each little ring that I have has an area to it. So if I look here, this little ring here has area. So I say to you, well, what is the area of that? So if we look here, can we take the circumference of each ring? That's how wide or how far it is around the ring itself. Isn't that its first dimension? And then multiply it by the thickness of the ring. So the thickness of the ring is dr thick. So the area, the change in area, this little dA, this little ring here, the area of that's going to be the circumference times the other dimension, which is the thickness. Very similar to finding the volume of a can, I use area times the height. You always use the dimension before it multiplied by the other dimension. So here we have a linear type idea multiplied by a thickness. This is kind of like a length times a width type idea. All right, so now that we have that, we know that dq and the density are related like this. So the density is going to be equal to dq, and instead of writing dA here, now I can write actually what it is. It's 2 pi r dr, like so. All right, now that we have this, we know that dq is going to be equal to sigma. Let me put the sigma first. So we've got sigma times 2 pi r dr. All right, now we've moved this step in the right direction because we hate that dq in there. There's nothing we can do with it. So we've got to eliminate it, and we always use density to make that conversion from the dq into something that we can actually measure, like the radius of the disk itself. All right, now, it's time for the little trick. All right, now, if I think about this, I could go back all the way back at the very beginning and derive this from scratch. But don't I already know the electric field because of a thin ring? So when we look at that little wire that was around, like forming a little hoop, isn't that actually a thin ring of wire? Well, that's exactly what I've drawn here. So I can think of an area as a whole bunch of those hoops. Bigger, 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 bigger. And if I keep adding those up, I can actually end up with an entire disk of charge. So instead of starting from scratch, I wrote down the formula that we derived for that thin ring of charge, that hoop of sorts. So when we look at this, we can take this formula and apply it now for our new situation. All right, now, the electric field in this particular one, all right, or the contribution by each ring, all right, we'll call this dE, and we have 1 over 4 pi EO, epsilon naught, and instead of writing, I'll put the Z here, instead of writing Q, I'm going to put dQ in there, and then divide it by Z squared plus big R squared to the 3/2. All right, so I've changed nothing here, but what I've actually figured out is what the little contribution is for each ring in that disk. So dE, that contribution that's made to the overall electric field by each ring, is going to be equal to this, which is dQ. All right, now we know that dQ is actually equal to this. So let's rewrite it. So we have dE again, the contribution from each ring, 1 over 4 pi E epsilon naught Z, and instead of writing dQ again, I'm going to write sigma, all right, and then we have 2 pi r dr. And then that's going to be divided by Z squared plus big R squared to the 3/2. All right, now we could eliminate a couple things here. We've got a little bit of work to do. All right, so I'm going to eliminate a pi here, like so we can cross the pi off. So we end up with something that looks like that. All right, now my inclination is to take the 2 and the 4 and cross off the 2 and end up with a 2 in the denominator. But I'm not going to do that for a reason later for the purposes of the calc problem and actually solving the integration itself. So let's just clean this up a little bit. So I end up with dE is equal to 1 over 4 pi epsilon naught. We've got z. We've got sigma, which is the charge density. And then we end up with 2r dr, something along those lines. And then that's all divided by z squared plus r squared to the 3/2. All right, now we've got to go back, and it's time to start our integration process, which we'll do.